All right, welcome back to Real Analysis. Continuing our work in Chapter 5, we're going to take a look at a notion related to continuity. It's a little bit stronger of a notion called uniform continuity. All right, so to kind of motivate it, I'm gonna kind of use this picture of an example we've talked about before. Let's look at this function f on the open interval from 0 to 1 that's just defined by f of x is 1 over x, okay, the reciprocal function. I've got a graph of it drawn there in the picture. Okay, and we've shown that this function was continuous. All right, we gave an epsilon delta argument of it. I think I did it for a specific x, and maybe I didn't restrict it to the interval from 0 to 1. But we've looked at the essence of an argument that shows that if you give me some number between 0 and 1, and you specify a positive number epsilon, it's possible to find some delta so that if x stays within delta of x naught, then the function value will stay within epsilon of f of x naught. Okay, so that is that it's continuous. F is continuous at x naught. Okay, and what I want to use this picture for is to kind of indicate that that delta depends both on epsilon and x naught. Okay, so I've tried to use some color coding here, and I don't know how successful we'll be in looking at this, but let's try to look at it. So I've got two different points, x naught and x1, drawn down here. Let's look at x naught first. Okay, so here's my f of x naught. It's the y coordinate on the y-axis of the corresponding point on the graph, and I'm looking at a given epsilon neighborhood of it. So epsilon is half the width of that interval that I've highlighted in the red laser pointer there. Okay. And then what am I doing? I'm basically kind of looking at f of x naught plus epsilon and f of x naught minus epsilon, finding the corresponding points on the graph and coming down and seeing what interval around x naught that I'd have to stay in order for the outputs to stay in that interval around f of x naught. Notice that that thing's not symmetric around x naught. I mean, it could be a feature of my picture, but in general, it won't be. So I'm taking delta to be the smaller of those two distances. So if you like, my first delta is this part that I'm highlighting over in red right there. And then I just kind of move by that same delta to the right. So staying within delta of x naught will guarantee that I stay within epsilon of f of x naught. Okay. And then I just kind of want to walk you through the same thing. I'll sort of switch the laser pointer color. Here I've got this point x1. This epsilon neighborhood that I've drawn around f of x1 is supposed to be the same width. Okay, so let me write it here. That the epsilon is the same in both of these intervals. So I'm looking at the same kind of tolerance around the output value, if you like. But this time, because x1 is closer to 0, when I look at the corresponding intervals that I have to stay in order to hit that epsilon tolerance, excuse me, it's skinnier. Okay, so in particular, again, it's not symmetric around x1, but if I take the minimum, it's just this little teeny green piece. So that green piece is much shorter than the delta that goes for the x0, right? So my point in this picture here is that the delta that goes with x1 is smaller than the delta that goes with x0. So that's what I mean when I write this, that the delta in general in the continuity definition depends on both. Depends on the tolerance you set, but it also depends on the point that you're looking at. Okay, so that's just kind of an observation. And that observation is supposed to make it be a little bit easier to digest this definition. So I'm going to say that a function is uniformly continuous. Uniformly continuous. So it has to be defined on some set A, and we're going to say it's uniformly continuous on that set if for every epsilon there's a delta, and the delta comes before you choose any input point. So for every epsilon, there's some delta, such that if you take any 2 points, x and y, whose distance together is less than delta, then the outputs f of x and f of y will be less than epsilon. So said another way, the delta here depends only on epsilon. It doesn't depend on the points that you're looking at the continuity at. Okay, so it's a subtly different definition, but it's important. So uniformly continuous is that there is, given an epsilon, There's one delta that will work across the whole domain. If you take any points x and y that differ from each other by less than delta, their outputs differ by less than epsilon. All right, so our function example above, the reciprocal function on the interval from 0 to 1, it's continuous, but it's not uniformly continuous because the delta will get smaller as you pick the x value closer and closer to 0. So there is no one delta that will work for every x. Okay, so this is our new notion, uniform continuity. It's an important notion. What we're going to do for the rest of this lecture is just kind of look at a couple of results about it. Okay, these are going to be sort of building blocks towards some theorems. Starting here very soon, we're going to start looking at some theorems that you were exposed to in your calculus course. This notion of uniform continuity, I would be surprised if it came up in your calculus course. So here's the first result. Okay, the first result is that if you take a function f and we suppose that it's uniformly continuous on some bounded interval, that is some interval like a to b, closed on the right, closed on the left, or just closed. Okay, if you have a function that's bounded on that, if you have a continuous function that's bounded on, my tongue is tripping, sorry. If f is a uniformly continuous function on a bounded interval, then the function is bounded. Okay, so uniformly continuous on a bounded interval means the function is bounded. Maybe I'll just scroll back up. Notice that for our non-uniformly continuous example, that's not true, right? This function, the reciprocal function, is continuous on a bounded interval, 0 to 1, but the function certainly is not bounded. So the interval, the domain is bounded, but the function isn't. The theorem I want to prove to you says that if you took a uniformly continuous function, that can't happen. A uniformly continuous function on a bounded interval will always be bounded. Okay, so let's take a look at our proof. The proof starts off by saying, okay, well, suppose I've got some bounded interval. There's 4 flavors of what that could be. It means you have some endpoints, A and B. Let's say B is bigger than A, and I is one of these 4 kinds of intervals. Okay, so I don't have to specify which one, but it's some bounded interval. So it's some interval between 2 numbers. And then let's use the uniform continuity. So take the epsilon to be 1. So uniform continuity says that there's some delta, depends only on that epsilon, so that for any 2 points x and y in the interval, if x and y differ from each other by less than delta, then the function outputs differ from each other by less than 1. Okay, so I'm finding some delta that's true. Now I'm going to construct the bound. I'm going to use some kind of familiar looking notation from calculus. So first of all, this is a little bit out of a hat, but you'll see where it comes from. Use the Archimedean principle to pick a natural number that's bigger than 2 times the width of our interval over that delta. Okay, that's a positive number. There's always such an n. And if that's true, just kind of rearranging the inequality, then the width of the interval over n is going to be less than delta over 2. Okay, I'm going to use some familiar calculus notation and call that b minus a over n delta x. Okay, thinking of it kind of like a step size, like when you saw integrals in calculus. And then also like when you saw integrals in calculus, I'm going to define for I between 0 and n, the number xi to just be a, the leftmost endpoint, which may or may not be an I, depends on which of the 4 kinds of intervals we have. But I'm going to let xi be a plus I times that delta x for I between 0 and n. So the picture should guide us here. Right? According to that definition of xi, stop the video and look at the details at your own speed. But x0 is just the number a. And then x1 is sort of one step to the right of that. And how big is the step? The step is delta x. x2 is another step, also of delta x, and so on. So every one of these subintervals, xi to xi, xi minus 1 to xi, has the same width, delta x. And if you add this step size, b minus a over n, to a n times, when I is n, you can stop the video and check that x sub n is going to be the endpoint b, which again may or may not be in the interval. So all of these endpoints, x1, x2, and so on up to xn minus 1, they all belong to this interval for sure. A and B may or may not belong to the interval, depending on which of the four kinds we have. Okay, if it's closed on both ends, they both do, so on and so on. Good. Okay, so what have I done? I've covered my interval I in these little subintervals, each one of which has a width that's no more than half of our delta. Okay, so why do that? Well, if I take, say, for I between 1 and n, so starting with x1 and ending up at xn, it could be any one of those things. If you pick x to be in any one of the subintervals, but I need it to be in the domain, so that's why I'm intersecting it with I. Again, that's kind of vestigial unless the subinterval I'm picking is this one and A is not in there. So I just don't want to pick X to be A. Or if the subinterval is this last one and B is not in there, I don't want to pick X to be B. But that's why I'm intersecting it with I. So I take that subinterval. This is the one I'm imagining. All those points are in I. Then if I pick any X in that subinterval that's in the domain, its distance from Xi, the right endpoint, it can't be any more than delta. Well, that's because if you pick an x in this subinterval, any 2 points in this subinterval differ by, at most, delta x. Delta x is less than delta over 2, which is less than delta. Okay, so my uniform continuity definition is met. If I pick x in that subinterval and it's in the domain, its output from f of xi can be no more than 1. Okay, can be no more than 1. So unpack the absolute value and rewrite that expression like this. Here, I'm going to admit that there's a little bit of a notational flaw here. Like if B, for example, does not belong to the set I, capital I, and this xi is if I is equal to n, then I'm writing f of b, and b isn't in there. So I don't want to make the proof notationally more complicated. But if that was the case on that last subinterval, then instead of using xi, I would use xn minus 1. So if b is not in there, then just use xn minus 1 here instead of xn. The same principle would be true. Any point in that subinterval would be less than delta away from the left endpoint as well as the right endpoint. Okay, so there's just a little notational admission I'm putting in my proof here that depending on those cases, but I didn't want to write a bunch of cases. This is the spirit of the argument. Okay, so what have I done? I've found out that my function f is bounded on each one of those subintervals, right? Why? Because look, on any subinterval, the function's output is at least this number. That's the left-hand endpoint of the subinterval, or the right-hand endpoint of the subinterval, sorry, minus 1, but it's no more than its right-hand endpoint plus 1. So it's bounded on the subinterval. So if it's bounded on that subinterval, then its infimum and supremum of the outputs have to exist and be real numbers. So let's let little mi, I'm talking about each I between 1 and n, let's let it be the infimum of the possible outputs for the x's in that subinterval. Because it's bounded, that infimum exists and is a real number. Okay, so it's not negative infinity, quote unquote. Likewise, I'm going to let capital M be the supremum of the outputs on that subinterval. This thing's a bounded set, so that supremum exists and is a real number. So for I between 1 and n, I get these n values of little m and n values of capital M. There's a finite number of them, so I can let, say, little m be the smallest of all the little m's and capital M be the biggest of all the capital M's. Nice. Well, little m and capital M are going to do the job. They're going to bound our function, because if you give me any x in I, well, it has to be in one of those subintervals. It might even be in more than one. If it's an endpoint, I don't care. Pick one. Pick one that it's in. It has to be in one of those subintervals. Okay? That's true for all I between 1 and n. So we just said that f of x, well, f of x is certainly at least the infimum of that set and no more than the supremum of it. Every element of that set is at least its infimum and no more than the supremum. But little m is the minimum of all those infs, so it's less than or equal to mi no matter which I you have. Likewise, capital M is the maximum of all those sups, so it's greater than or equal to mi no matter which I you have. And so that shows that the function value f of x is in the interval from little m to capital M. So our function is bounded on I. Nice. Okay, so stop that and kind of go back through it at your own pace and sort of pick it apart. Maybe fill in the case of the proof that in my construction, if my interval here did not contain the point B, you can kind of go back and fix the notation there. Put in that case. Nice. Okay, so a uniformly continuous function on a bounded interval is a bounded function. Nice. The next result, also important in our future work, work in the near future, is that if you take some closed and bounded interval, so this time I'm going to be very specific about what kind of interval I'm talking about. If I take a closed and bounded interval, aka a compact set, a compact interval in the real line, then if you have a continuous function on it, it has to be uniformly continuous. This one's a super important theorem, that if you are continuous on a closed and bounded interval, then you're uniformly continuous on that interval. Okay, so let's try to walk through the proof of this one. Stop the video as I go. I'm talking a mile a minute, but you can take advantage of the fact that you're watching this on YouTube and stop it and think about each thing I say, justify it. So get out a blank piece of paper and a pencil and kind of do this proof with me. Don't just passively listen to me talking about it at a million miles an hour. That won't do much good. So I'm going to kind of give an indirect argument. I'm going to suppose for a contradiction that I've got this function on this closed interval a to b. I didn't quantify a and b here, but I could throw it in there. So here I've got two real numbers, a and b, and I'm assuming that one is less than the other. And I've got a continuous function f on that closed interval, but suppose that it's not uniformly continuous. So this is where I'm looking for a contradiction. So I'm going to suppose that I've got some continuous function on this closed interval, but it's not uniformly continuous. Here's the part that I really hope you'll stop and kind of maybe even try to do before I say it, because we have a definition of uniform continuity above, and I'm assuming F isn't it, so I've got to negate it. So this is one of our fundamental skills in the course, is being able to negate these complicated quantifying definitions. So if you're not uniformly continuous, then there has to exist some positive real number epsilon, right? Such that no matter what delta you pick, for all delta, it's always possible to find at least 2 points, x and y, in the domain a to b, such that x and y differ by less than delta, but the function outputs differ by at least epsilon. So that's just carefully negating the quantified definition 5.46 of uniform continuity, right? So I hope you stopped it and thought about that. So if that's true, if there's some epsilon that this works for every delta, then I can take delta to be the reciprocal of any natural number. Okay, and I can find points. They depend on this natural number, so I'm going to call them xn and yn. I can find 2 points in that interval that differ by less than 1 over n. They differ by less than delta, but the function values there differ by something that's at least epsilon. Okay, so that gives rise to a couple of sequences, xn and yn. I've got these points in my closed interval for every natural number. Those are sequences. And in particular, the difference sequence, because we've set it up that xn minus yn in absolute value is less than 1 over n for all n, then that difference sequence converges to 0 as n goes to infinity. Yeah. The difference of xn and yn is less than 1 over n for every n. 1 over n will become less than any pre-specified positive number. I don't want to call it epsilon because that's already playing a role in my proof here. But that sequence xn minus yn converges to 0. Stop the video and put in a detail if you need to. Okay? Okay. So now just focusing on the xn's, it's a sequence in the closed and bounded set A to B. It's a compact set. So that set has the Bolzano-Weierstrass property. That's what 4.21 says. So because we have a sequence in a compact set, the Bolzano-Weierstrass property says that there's a subsequence, I'm going to call it xnk, of that sequence xn, that converges to some point in that set. So not only does this subsequence converge, it converges to a point in the interval to A to B. Okay, so I've got this subsequence of the x's that converges. Well, for each term of the subsequence, I can look at the corresponding term in the sequence of y's. So that gives me some subsequence of the difference. So xnk minus ynk is a subsequence of xn minus yn. Uh, and that subsequence is going to converge to 0 as k goes to infinity, because every subsequence of a convergent sequence converges and it has the same limit. Okay, cool. So now I'm going to use some algebra of convergent sequences applied to these subsequences. Certainly for every k, ynk is the difference of xnk and xnk minus ynk. Stop the video and do the math, right? And because of that, we have limit properties that says that this thing, this difference, xnk, it's a convergent sequence. It's a subsequence, I know. Xnk minus ynk is a convergent sequence. Okay, so their difference converges to the difference of their limits, that is to z minus 0. So this ynk sequence also converges to z. Okay, we've already said it, but let me write it again. That's some point in this interval a to b. Nice. But f, our function f is a continuous function. We're assuming it. So because it's continuous on that domain, you take these convergent sequences, xnk and ynk, the image sequences have to converge to the image. Z is in the domain, so that makes total sense. F of xnk converges to f of z, f of ynk converges to f of z as k goes to infinity by the continuity of f. But for every one of these k's, by the construction above, remember that epsilon, the outputs of these two things, those are just among the sequence terms xn and yn, xnk and ynk are some of them. And we said that the difference of f of those sequence terms was at least epsilon for every possible sequence term. So in particular for the terms in this subsequence. All right. So if we use some more limit laws, I'm applying it here. I've got this absolute value of the difference of those two things greater than or equal to epsilon. So if I remember correctly, 5.19 says the limit of absolute values is the absolute value of the limit. And 5.23 is one that says that the inequality is preserved. So you can stop the video and check those. So taking limits of what I underlined in red there, I get that the absolute value of f of z minus itself is greater than or equal to epsilon. Epsilon was a positive number. But that's our desired contradiction, because the absolute value of f of z minus itself is 0. So we've deduced that 0 is bigger than 0, strictly bigger than 0. That's a contradiction. Okay, where'd the contradiction come about? It came about from us assuming that f wasn't uniformly continuous, so therefore f must be uniformly continuous. Whew, good. Hopefully you stopped the video a lot and kind of soaked that in. That's my best attempt at presenting that argument. We're near the end here. I want to make a remark that what was crucial about the domain being a closed bounded interval is that it had the Bolzano-Weierstrass property. Any compact subset of the real line has the Bolzano-Weierstrass property, any closed and bounded set. So the exact same proof would show that if you take f defined on any compact set, if it's continuous, then it's uniformly continuous. So it doesn't have to just be a closed interval. It could be any closed and bounded set, that is any compact set. That's one remark I wanted to make. And then we're going to end this theorem, or this lecture, by kind of putting those results back together. The two results in the theorem, we've shown that if you have a continuous function on a bounded interval, that it's bounded. And we just said that a continuous function, or uniformly continuous function on a bounded interval is bounded, but every continuous function is uniformly continuous on a closed interval. So if we put those together, we get theorem 549. That if you take a continuous function on a closed bounded interval, then it has to be a bounded function. Okay. So in other words, our opening example, you couldn't create such an example on an interval that had endpoints. You can't write a continuous function down on a closed interval, bounded closed interval, that would have sort of an asymptote in it. Okay, so how do we prove it? Well, we'll just put our results together. If you take some continuous function on this closed interval, we just proved that that is uniformly continuous. That was what 548 said. But we said that if you take a uniformly continuous on a bounded interval, then it's bounded. That's what 547 said. So you just stick 547 and 548 together, and you get a proof of this theorem 549. And I'm going to end this technical lecture video by saying the same remark, that you could replace the closed interval in the statement of theorem 5.9 with any compact set, any closed and bounded subset of the real line, and all of those results are going to go through. Okay, thanks for listening.